Okay, so we are going to take a look at the contribution of specific heat from phonons. So we're going to define a few things first. One is that we're going to have n, where n is the number of particles we're dealing with. So for us, we have the total number of ions, and this is going to stay consistent. We are going to consider this little n instead, though, too. This little n is the number per unit volume, because this is going to make our calculation just a little bit easier. We have to worry about a thing called k. We're in k space, and our k is a k vector. So a k vector is that momentum vector that we're going to be dealing with, and we're going to have to be dealing with all the different k vectors for every different particle we have here. We have S, which is the branch, or the acoustic branch, for our phonons. We have 3 of these because we have 2 transverse and 1 longitudinal phonon. And these are all going to depend on each and every single k vector we have as well. We are going to have something called omega s of k. Omega s of k is the frequency of a phonon. And this frequency of phonon, it depends on the branch of the phonon, and it depends on our k vector for every single individual particle here we're dealing with. And a phonon then would thus have an energy h bar omega s of k. That's going to be our energy of a given phonon.
All right, so our ultimate goal is to find the specific heat capacity due to these phonons. And to start off with that, we need the Hamiltonian of each harmonic oscillators. So our total internal energy is given by U. Okay. U is the sum over all S and sum over all of k vectors times h bar omega s of k times n, s, and k plus a half. All right, so now this is the total energy per unit volume. What is all this? Because our phonons are quantum oscillators, each phonon acts like an excitation. So n of s and k is n of s and k is like the phonon. And because phonons have no spin and they are classified as bosons, they follow Bose-Einstein distribution. So this then equals 1 over beta h bar omega s of k minus 1. All right, so, and as we all know, from the constant volume heat capacity is just the derivative of the total energy with respect to temperature. So C equals respect to temperature given a constant volume equals 1 over B times T of this fantastic looking thing. S sum over K. All right, so we can fairly easily take the derivative of this. S. Okay, the half does nothing. Okay, so now the fun part is trying to find this thing right here. Often it's just easier to leave it in a form that looks like this, so S and K. E to the H. Sometimes it's easier just to leave it in a form like this and then take approximations. But if you want to explicitly take the temperature derivative, it's going to look like this. So okay. Minus 1 all to the minus 1. So -1 goes out. This becomes a 2. You'll get an S. Okay. Get one of these things on top, and then keep forgetting the B. And therefore, these get a positive. And finally, And there's 1 over Boltzmann factor here. And from here, we generally go to make approximations, like low temperature, high temperature, intermediate.